Hello and good morning, everyone. I'm Fatima from Team 2, which led by Dr. Yu. And as he mentioned, so our project will be on GeoAI for burn area analysis and wildfire risk mapping in the Pantanal wetland. Pantanal wetland faced with the early season wildfire in 2024, which caused by drought, extreme condition like drought and land change model. So that's why this kind of two important question came up to our group. So we are following to answer these two questions. First, how do environmental and land use factors influence burn extent? And the second one, can GeoAI enhance early stage fire risk mapping to support proactive management? So we faced some of the challenges. One of the main important one was highly imbalanced burn and no burn data set. And we only had one early dry season, dry summer season, and also burn occurrence not tightly connected in space and time. So for shape our direction, we started to brainstorm. The first question that we think about that, how can we incorporate space and time in our modeling? And what kind of model can capture the burn context perfectly? And how can generalize and how can we improve the generalize our model? And the last things that we think about it, that was like feature engineering. What kind of feature can improve our model? So our group following two main approach. The first approach that was the base line modeling, that was the based on the tabular data set. So our model, the classifier, the random forest and XGBoost was run by using the physical feature for predict burn and non-burn area. The second one, we add the burn fire history. For example, we want to know how many pixel burn within the 5 by 5 area over the last few days. And lastly, we add the alpha Earth embedding data set for adding the more context physical environment and ground environment to our model. So the second main approach that we followed, that was the spatial and temporal sequence modeling. So instead of just looking ahead at the isolated area in a pixel, we are trying to focus on the patches over the last few days and um, predict the wildfire in the patch center. So now I'll hand it over to my teammate, Daniel.
Hi, everyone. I'm Daniel with Team 2. Um, so just to first talk about a little bit of our basic features. So we use things like land cover, elevation, temperature, dew point, wind speed, total precipitation, soil water content, and surface pressure as our basic features across all tabular models. Next, what you see up here is the kernel extractions. So lag 1, T minus 1, T minus 2, and so on. And it really starts to give the models that spatial temporal context to be able to better predict the fire. And then lastly, we use the channel embeddings of Alpha Earth. And so this really helped increase the resolution of some of the things like land cover and elevation and give it more context, a little bit more about fuel connectivity, and so on. I think one of the limitations was that it's only 1 year right now, and so it's still a very high resolution. And then to talk a little bit about our results. So first, I think we should focus on basic features to basic and previous burn again. So you can see that by including the previous day's burn, we really start to see that the model is improving. And then similarly, when we add the alpha I embeddings, the model improves further, right? And then when we analyze the random forest XGBoost and the TableNet, which is a neural network with attention, we see that the XGBoost model performed the best across this. However, I do want to mention that this is a one-to-one burn sampling. And so reality, like we said, we didn't have that ratio. It was, a very high burn to non-burn ratio in real life. And so we use this to better train the models to be able to detect that. Otherwise, the signal from the burn would be drowned out. And so then when we predict across the single day, we see again that we have better error metrics as we progress along inclusion of more features. But also we have mixed results with XGBoost not being the best model. on most days, on the day. So random forest with previous burn and the alpha I embeddings ended up outperforming both the XG boost and TableNet, whereas XG boost just with the basic features drastically outperformed the random forest and TableNet.
Hi, thank you. So we have been seeing a lot of numbers as for now. So okay, no problem. So yeah, so we have been here, seeing a lot of numbers, but I'm really fond of the actual maps, what the extents are and how it actually looks in its actual conditions. So this is the results from the from our basic feature model. On the left-hand side, we can see the burn probabilities. The middle one are the actual predicted burn areas, and the right-hand side are the actual ground truths. So we can see that using only the basic features, uh, it's not doing a decent job in predicting the burn areas. We can see there are lots of block areas, there are some artifacts. These are mostly coming from the climate data sets. As soon as we added the previous burn histories, we can already see that, yeah, the model has improved a lot. There are no artifacts, no block areas, and it can capture those special patterns as well. So we went a little bit further to push our model to the next step and also added those alpha embeddings to see if it can do even better. So we can, here you can see that, we can see that, yeah, the results are better, but not to that much improvement to the previous one. But we can see that, we can say that, yeah, the alpha embeddings has a lot of importance in actually detecting those burn areas. And if we look into the feature importance for the basic features, we can see that the topographies are topography is the one that dominates. But as soon as we added the burn histories, those variables are not the dominant one, and sorry. Okay, so this lag one is the previous day burn history is comes at the top. So our conclusion is that not the topography, not the climate, the burn histories are the most important feature that we should focus on when predicting predicting the burn areas. So these results are including all the features we have. We tuned the model and see that how the features looks like for across all the models. And we can see that the different models tends to give priorities on different features. But our conclusion is it's not any single feature, not any single model. It's the interaction between each features or each variables. So that's how the model learns. Thank you.
Not yet. And I'm Jiyeon. Sorry. Oh, no way. Oh. Oh my God, what happened? Let's move on to the second approach. The main difference between the previous one and second approach with the convey LSTM is that the baseline is trained on pixel level, but the convey LSTM is trained on raster level. It means that even though the previous one also tried to use the spatial temporal context like previous one, but convey LSTM do it more explicit way. And this figure shows the difference of them. So we can, unlike the scattered prediction result of the previous one, we can see that continuous continuous prediction area. It aligns with the nature of wildfire itself. It means that continuous phenomena. And also, I wanted to say is that we mentioned that one of the challenges of our data set is the discrete characteristic. But we think that in future, we can use this continuous area prediction to handle this challenge.
So to wrap it up, like what we done is like we built 4 different models, and we tested different combination with several experiments, different inputs, patch size, and spatial temporal features. And what we found is like we predicted all the early stage fire, and we have achieved satisfactory accuracy for the test data, but there is way more work to tune the model for the single day prediction. For concerning like the we find also that the burn history, the spatial temporal of the burn history, is among the most important predictive. And the embedding like alpha AI improved the prediction accuracy, possibly representing prior status of what land cover at that year was representing. So what is needed to enhance fire prediction in that case? Because we find the burn history was at most important, we suggest that autoregressive architecture could be a very promising way forward for operational models for fire prediction. And we also think that since the literature always report that the fuel status is the single most important environmental predictor, but the data is a limiting factor, AI embedding like alpha AI is a great potential to fill this gap, but there is 2 major challenges. The first one is the interpretability of what are these bands that are important. So we need more experiment to figure out what do they represent. And also the temporal frequency. So these are single layer for 1 year. So perhaps producing such data on like monthly level or more coarse temporal, more higher temporal resolution. So our last insights, like for like our pivots, what didn't work too, like we took downloading this data, also took several attempts with different resampling, constructing this relevant feature, figuring out the spatial temporal of the burn history took another 2 days. The experiment with the spatial temporal sequence model, more than 4 days, still going. Struggle with the computing platform and going back and forth, and the result is still running actually. But luckily, like teamwork, different perspective made it work. So thank you for the great opportunity.
Okay, thank you, Group 2, for the great presentation. I'm curious, what is the way that you integrate the alpha embedding in the convolutional LSTM? Did you like stack them as additional bands, or you concatenate them like at the inference stage?
So could you say one more time?
So how did you use alpha embedding in the convolutional LSTM?
The alpha embedding is not used in the Conv LSTM model. It is only used in base model. So in training Conv LSTM model, we only use the DEM for including terrain.
So then are you considering using the like alpha
Of
embedding?
course,
Yeah.
we want to try, but the data set is too big to run the model before the deadline. So we will do try.
Yeah, that makes sense. Yeah. And like one more thing, maybe like to do some future learning, because like I think one example they show like in the DeepMind's like web pages that like it's very useful for like future learning. Yeah. So yeah, we can discuss about it later.